All right, friends, this is my re-recording of Lecture 29 of Chapter 8.1. This is the first of three lectures in Chapter 8, which is dealing with experiments that we do to understand the kinetics of a reaction. And the reason I'm re-recording this is because what we did in lecture, the audio didn't get captured. So we're going to begin actually still in the end of chapter 7, where we're talking about reaction mechanisms and potential energy landscapes. And here I'm showing you a few different ways that we can think about reactions that have multiple reaction coordinates. So these examples are in the category of substitution reactions. And in a typical substitution reaction, we have two different reaction coordinates. By the way, in what we're going to see here, you've got sort of a side view of the reaction potential energy landscape, and here is an overhead view. In the side view, we can see the z and the x and the y axes. In the overhead view, we can only see the x and the y axes. And the potential energy axis, which is the z axis, we don't see in this overhead view. Now, in a substitution reaction where you're replacing a leaving group with a nucleophile, there are two things that are changing. The first is the formation of the nucleophile carbon nucleophile bond. So we're going to call this x-axis. Formation of carbon nucleophile sigma bond. And it's going to range in values from 0% to 100%, or 0 to 1. At this position, the nucleophile carbon bond is not formed at all. Here it's completely formed, and this might be some measure of the distance between the two. Similarly, in a substitution reaction, we have to break the carbon leaving group bond and the leaving group leaves. So along this y-axis, we've got leaving group leaves, or breaking of the carbon leaving group sigma bond. You got nucleophile attacks on the x-axis. You have leaving group leaves on the y-axis. And then on the z-axis, which we could represent here, on the z-axis, we have energy. Okay? So, and the orange surface is meant to show the variation in energy as we change the distance between carbon and leaving group, and as we change the difference between nucleophile and carbon. And this is the potential energy landscape for a methyl halide. I'll just point out that in this overhead view, again from 0, let's see, nope, that's not what I wanted to do. Thinking sort of from 0 to 1, this is nucleophile attacks. We form the carbon nucleophile sigma bond. And then here is leaving group leaves. we break the carbon leaving group sigma bond. And the molecules or species that we would have at each corner of this plot give a sense for what's happened as we go from one side to the other. For example, our starting materials are the methyl leaving group, methyl halide perhaps, and a nucleophile. If we only move along the x-axis and we form a carbon nucleophile bond, the intermediate we would get is this, where the methyl group is forming a bond both with the leaving group and with the nucleophile, where carbon nucleophile bond formation is at 100%, whereas carbon leaving group bond breaking is at 0%. If in contrast, we go from this corner with our starting materials only along the y-axis is breaking of the carbon leaving group bond. So at this corner, the leaving group is completely gone and we have a carbocation, and the nucleophile hasn't come in yet. The leaving group is 100% gone, the carbocation is 100% formed. The leaving group's 100% gone, nucleophile is 0% attacked. If we go from this corner with the carbocation along the y-axis, we form the new nucleophile carbon bond, and that gets us to our substitution product. So moving along this y-axis first to have the leaving group leave, and then moving along this x-axis to have the nucleophile attack, that is the typical SN1 reaction pathway. All right, so I'm going to highlight that with this orange arrow. That is the typical SN1 trajectory, and it involves a carbocation intermediate. Let's look at the plot to our left and see whether the potential energy surface reflects what we would expect for that SN1 pathway or trajectory. So right here is your starting materials. We're at the upper left-hand corner in the overhead view and in this back corner for the side view. And notice we're at a certain energy level. If we move only along the y-axis, we're having the leaving group leave first. I'm just going to highlight that by going up the hill, and then we get to the carbocationic intermediate. And notice if we were to sort of plot the relative energy level of that starting material, a line, we need to draw a line that's parallel to our axis. So actually, you know what I'm going to do is just, oops, didn't want to do that. See if this will work. I think maybe it, oh, no, doesn't let me. All right, we'll just try to do our best. This distance here is the energy difference between starting material and intermediate. And we can see that this is uphill in energy. So for this process, the change in free energy or the change in reaction enthalpy is positive. We see as well that there is a peak, a high energy peak, which is a transition state along this pathway. And we can see that energy difference would be whoa, I'm erasing too much, huh? That eraser was way too big. I didn't mean to do all of that. So this point is the transition state, and this energy difference here, activation enthalpy difference, is positive. And you can see that activation energy or enthalpy, in fact, we can just be generic and call it energy. I think that's probably better. We can see that it's uphill in energy to get to this intermediate, and that the activation energy is similar to the difference in energy upon going to the intermediate. And that's an example of the Hammond postulate. Okay? Then if we continue down this, continue now along only the x-axis, after the leaving group is left, we then allow the nucleophile to come in. And then we slide down this hill to our products. Okay. So that SN1 pathway, as mapped onto the just overhead view, we go down this y-axis first to leaving group leaves, and then we go here to the products. And so hopefully I'm trying to illustrate the flat surface that's a slice of this potential energy surface that corresponds to the SN2 trajectory or SN1 trajectory. You have this surface here along the y-axis. And then along the x-axis, you have this slice of the potential energy surface. All right, so the SN1 reaction, and if you unfolded this and just in general showed SN1 reaction coordinate, that would give you the familiar starting material, transition state, carbocation, and then product two-step reaction mechanism or energy diagram that you've seen. Now, let's talk about the diagonal approach. If we look at our overhead view, in the diagonal approach, in the overhead view, in the diagonal approach, the leaving group leaves at the same time as the nucleophile is attacking. It happens in a concerted fashion. We're simultaneously moving along both axes. And this is what happens, of course, in an SN2 reaction. The nucleophile attacks as the leaving group is leaving. And we can draw a representation of that in this way, right? And this arrow pushing mechanism indicates that you're forming the nucleophile carbon bond at the same time as you're breaking the carbon leaving group bond. All right, so this in purple represents the SN2 pathway. And that's illustrated by this other line, which for clarity, I am going to color purple. So we start from the same starting materials, but we move down the X and the Z axes at a similar rate so that we're forming the new nucleophile at the same time we're forming the new carbon nucleophile bond at the same time as the carbon leaving group bond is breaking. This point here is the transition state, and there's only one transition state in this reaction, and a reaction where you break the old bond and form the new bond at the same time, that's called an SN2 reaction, and this is our SN2 transition state. The typical SN2 energy diagram that we would draw is just this slice, which I'll attempt to show in purple, which is the this slice of the potential energy surface. All right. And I want to see a layering effect, so I'm going to recolor this in orange and have this layered over the purple, so you have an idea of what's in front versus what's in back. I know it's a minor thing, don't worry about it. Okay, now why do you suppose that, oh, sorry, let's just go ahead and plot along the diagonal the energy of the starting materials. This overall is going to be the activation energy for the SN2 reaction, and it's going to be greater than 0. I'm going to call this SN2. This one is going to be SN1. Also notice that this energy difference here is the free energy difference of the reaction, and it's less than 0, meaning the reaction's downhill and going from starting material to products. That's an issue of thermodynamics, and that is path independent. The only thing that matters for reaction thermodynamics is the stability of the starting materials versus the stability of the products. Now, let's ask, why do we suppose that the transition state for the SN1 reaction is so much higher in energy than the transition state for the SN2 reaction? And your intuition from introductory organic chemistry is that the methyl carbocation is very unstable because it doesn't have any nearby electron donating alkyl groups that can stabilize the positive charge by mixing with the empty p orbital on the positively charged carbon. So this carbocationic intermediate is so high in energy that the transition state leading to it by the Hammond postulate is also high in energy. And they are structurally similar. And that means that the lower energy pathway is to go over the SN2 trajectory. Now, one thing we haven't mentioned is why don't we have another reaction, another type of SN1 reaction where we first have the nucleophile come in to make a bond and then we have the leaving group leave. This would be an associative mechanism. And it's okay for some atoms, but carbon is too small to form 5 stable bonds. And therefore, this point at the corner is not a minimum or a saddle point on our potential energy surface, so we don't really ever populate this corner. All right. And so what you're seeing here is the transition state for the SN2 reaction. Has a certain percentage nucleophile attacking and a certain percentage leaving group leaving. In contrast, if we're to plot sort of where the transition state is for the SN1 reaction, the transition state of the rate determining step, it would be right here, which is like X percent, I don't know how much percent leaving group leaving, but 0% nucleophile attacking. Okay, Now, that makes sense, and it's basically just another way of illustrating what you learned in introductory organic chemistry. But what we want to do now is see how increasing the level of substitution of the carbon that bears the leaving group, how that affects our energy landscape. And it's going to do so in a way that tracks with what you would expect for these kinds of reactions, what you would expect for substitution reactions. So now our starting material is the ethyl halide and the nucleophile, and that's here. That's roughly at the same starting point. And we'll just assume that this energy difference between our starting materials and our products is about the same. So reaction thermodynamics are basically the same. But as we compare one to the other, I'm going to draw the energy of the starting material here, and we'll use this color blue. Oops. Maybe I like a lighter color blue, huh? I'll use this color blue to represent the activation energy for the SN1 reaction for the ethyl halide. And we're going to compare it to the activation energy that we got from the methyl halide. So that's this number in black. And you can see that the transition state, looks as though I needed to, make that line a little bit longer there. You can see that the transition state energy to go from is a little bit lower. To go from the transition state energy to go from the starting material to the ethyl carbocation is a little bit smaller than the energy to go from the starting material to the methyl carbocation. All right. So I'm going to just keep this. We might need this arrow a little bit later. So SN1 pathway, and this is for the methyl leaving group. And just for fun, I'm going to copy this and paste it here so that we'll sort of remember. Not enough space. So that we'll remember the difference in activation energy for the ethyl leaving group. You can see that it should be a little faster for the leaving group to leave. And the reason for that is that the energy difference between the reason for that is the carbocation at this corner has moved down in stability, or rather it has moved lower in energy. So the difference in energy between starting material and the ethyl carbocationic intermediate is lower. The difference is less uphill than it is to go to the methyl intermediate. So effectively, we've taken this corner and pushed it down in energy. This is where it used to be. This is where it is now. Okay, and that's because of carbocation substitution. So what that does is it makes the SN1 pathway a little bit more favorable relative to the way it was for the methyl halide. But notice the interesting change that this does to our reaction coordinate energy landscape. Having this corner lower in energy actually pulls our saddle point for the SN2 reaction a little bit over. So now our SN2 reaction pathway isn't a straight diagonal. In fact, at the beginning, it looks like we are breaking the carbon leaving group bond more than we're making the nucleophile come in. And notice that the energy height of the transition state for the SN2 reaction got higher. It was here, it's now here, and the reason for that is presumably steric hindrance of the nucleophile coming in. Okay, and in our overhead view, we see that the effect of moving this corner of the plot down in energy is that our transition state moved perpendicular to this diagonal line. And so we have something that actually now has a little bit more leaving group left and a little bit less nucleophile attacks. You see how we've moved from here to here. All right. And so we can continue onward. Once we get, for a secondary alkyl halide, you can see that the transition states for SN1 and SN2 are competitive. And we can see that because, again, we've lowered the free energy of this carbocationic intermediate, we have pulled the reaction landscape, the trajectory for the SN2 reaction even more towards towards this corner. And so now we're even less nucleophile attacks and even more leaving group leaves. Notice that these are all, the purple trajectories here are all SN2 reactions, but some are starting to have transition states that are looming ever closer to an SN1 type reaction. And of course, once we get to the tertiary alkyl halide, let me just try to uncrop that a little bit so you can see the tert-butyl group. Oh, forgot to press the check mark. You can see that now, relative to the secondary carbocation, we have moved the carbocationic intermediate even lower in energy. That lowers the energy of the SN1 transition state, and that makes the SN1 pathway now competitive with, and in fact, lower in energy than the SN2 pathway. Notice that the SN2 pathway transition state is now higher in energy than the SN1 pathway, and that is because of steric hindrance as we approach from the backside. Again, another interesting feature is that the transition state for the SN2 pathway has again moved to become even more SN1-like. That is, even less nucleophile attacking and even more leaving group leaves. So interestingly, you can use this type of plot to give you a sense for how changing the starting materials of a reaction might change the mechanism of the reaction and even the character of the transition states. one of the things that we've seen is that when you lower the energy of a point that's not along the diagonal, that tends to pull the transition state that is on the diagonal towards that corner, perpendicular to the diagonal, right? So lowering the energy of the carbocation we saw shifts the position of our transition state in a way that's perpendicular to the diagonal. You can think of this as though this potential energy surface were some kind of sheet, and you had a marble sort of laying right here in the middle. If you lowered this corner, the marble would tend to move towards the place where you had lowered it. One thing we haven't talked about is what happens when you change along this diagonal, the starting material to product. See, here we're changing the energy of an intermediate, and that'll pull the transition state this way. If we change the energy of a starting material or a product, then the changes are going to be governed by the Hammond postulate. For example, if let me just be clear. If we were to raise the free energy of this corner, we would also tend to push the mechanism in this direction, right? Okay, for the starting material or products corners, if we change their free energy, it's going to have an effect consistent with the Hammond postulate. So if we increase the free energy of the starting material, that's actually going to have the effect of moving our transition state towards starting material. If the starting material and the transition state are closer in energy, as we bring this closer in energy to this one, to the transition state, they have to be necessarily similar in structure. If we decrease the energy of this corner, that's going to tend to make the transition state more product-like. And we'll just be clear, you can do this with the products as well. If you increase the free energy of the products, that's going to make the transition state more product-like. If you decrease the free energy of the products, that's going to make the transition state more starting material-like. So for the corners that are off the diagonal, you've got this marble effect. For the corners on the diagonal, you have this Hammond postulate effect. All right. So now we're prepared to deal with a situation. I'm just going to copy this energy diagram, and let's imagine how you'd expect the transition state to change if we made some change to this system that we haven't discussed before. So I'm going to erase everything that we've drawn on this molecule before. All right. So let's imagine that we get a better leaving group. We make the leaving group better. That would presumably mean that the negatively charged leaving group moved down in free energy. And so, and since the leaving group is also one of the products, that would be moving this corner down in free energy as well. Okay? So based on what we talked about earlier, and by basically the same amount. based on what we talked about earlier, if we lower the energy of this corner, the transition state for the SN2 reaction is going to be pulled in this direction, perpendicular to the SN2 trajectory, which, sorry, I will highlight in purple to be consistent with what we've done before. If I lower the free energy of the products, that should make the starting material, the transition state, closer in energy to starting material than to products. So we would expect the transition state to become more product-like. Okay? And we would expect those two effects to combine and add together in basically vector format. And so the overall effect that we expect to see here is the vector sum, which would be something like this. Right? And we can do that simply by, yeah, basically there. All right. And so our new transition state, if we lower the free energy of the, and we don't have to get the vector math exactly right, if we lower the free energy of our leaving group, our new transition state, notice the effect is basically the same amount of leaving group departure, but less nucleophilic attack than what we had previously, right? So the overall effect moved us towards less nucleophilic attack and not to more leaving group departure, which is a little bit interesting. It's sort of counterintuitive to what you would expect. Let's similarly consider making the nucleophile more reactive. Hold on. Undo, undo. So let's similarly consider, making the nucleophile more reactive and see what that should do. Okay, if the nucleophile gets more reactive at this diagonal, that's going to mean that we go up in free energy, and that should make the transition state more starting material-like because of the Hammond postulate. That's the so-called Hammond effect. So we expect our transition state to move along that diagonal like this, right? However, if we increasing the free energy of the nucleophile would also increase the free energy of this corner. And by the marble effect, that would tend to push the transition state this way. And if we do the sort of vector sum of those two effects, we get something like this, where this is our new transition state. And somewhat counterintuitively, even though we have a better nucleophile, we have the same extent of nucleophilic attack, whereas we have substantially less leaving group departure. So, or what we might conclude is that when we have a better leaving group, we move our transition state to something that doesn't need as much nucleophilic attack for the leaving group to leave. And if we make our nucleophile higher in energy, more reactive, we change to a situation where we don't need the leaving group to leave as much before the nucleophile attacks. And That's good, solid reasoning. All right. So I've spent too much time walking you through that. It can be kind of confusing. I hope that was helpful. I'm now going to transition to chapter 8, and we're going to talk about a pretty important subject called kinetic isotope effects. And this is one of the ways you can try to figure out experimentally which bonds are changing in the rate determining step, in the transition state of the rate determining step. So the idea behind kinetic isotope effects are you're going to substitute hydrogen versus deuterium at a CH bond that changes during a reaction. And by changes, we mean either breaks or changes hybridization. And what we do is we replace, as I said, replace H versus D at a hydrogen versus deuterium at a carbon-hydrogen bond. Then we're going to measure the rate constant of a reaction with the CH bond, which we're going to call KH, and the carbon-deuterium bond, which we're going to call KD, little kd. And then we will compare the two. We'll divide KH by KD, and if that ratio is 1, we will conclude that the CH bond isn't changing much in the transition state of the rate determining step. In contrast, if we see that the rate is faster for deuterium than, faster for hydrogen than deuterium, we're going to call that a normal kinetic isotope effect. If it's between 1 and 2, we'll generally call this a secondary kinetic isotope effect. If it's between sort of 2 and 7, we're going to call that a primary kinetic isotope effect. And you can see primary kinetic isotope effects when you are breaking the XH versus XD bond in the transition state of the rate determining step. You can see secondary kinetic isotope effects when there is rehybridization, a change in hybridization of the XH versus XD bond in the transition state of the rate determining step. Or it may mean that the XH or XD bond is close to, but not exactly where the change is occurring. Okay. And then if we find that KH over KD is less than 1, we're going to call that an inverse kinetic isotope effect. And these are always secondary. And they are generally the result of rehybridization of a CH versus, or of an XH versus XD bond in the rate transition state of the rate determining step. Now, we need to try to figure out what the physical basis is for these kinetic isotope effects before we start trying to interpret them in detail. And so I will just remind you of some things we talked about in the kinetic chapter. The reaction in general, the reaction involving the XH bond, should have a rate constant that is equal to some pre-exponential factor times the number e raised to the power of EH minus EH over KBT, where KB is the Boltzmann constant and EH is the activation energy of the reaction with the XH bond. And similarly, the rate constant for the reaction with deuterium is similarly equal to some pre-exponential factor divided by the opposite of activation energy for deuterium. The exponential factor raised to the power of the opposite of the activation energy for the reaction with the deuterium bond. And then KB is the Boltzmann constant. This is basically the same as the universal gas constant, only it's for individual molecules rather than moles. T is temperature. And I won't go through the math in really any detail, but if you divide KH by KD, this is your kinetic isotope effect, and it turns out to be the exponential of the opposite of hydrogen minus the opposite of deuterium activation energies, or in other words, the activation energy of deuterium minus the activation energy of hydrogen divided by KB over T. So you can see, and that's you can sort of see where the kinetic isotope effect comes from. We can get KH over KD is greater than 1 when activation energy for deuterium is greater than activation energy for hydrogen. We can get KH over KD equals 1 when activation of deuterium equals activation energy for hydrogen. And we can get KH over KD is less than 1 when our activation energy for deuterium is less than the activation energy for hydrogen. Okay, so that sort of makes sense. But now we need to talk about why we would expect activation energies to be different for hydrogen versus deuterium. And to do this, we need to consider a couple of factors. And that is that when you are breaking a bond in a reaction, the reaction coordinate represents really sort of a bond vibration. So for example, along this y-axis as the leaving group leaves, you could represent that as a vibration of the bond between carbon and the leaving group. And it turns out that energies of bond vibrations are quantized. And we're going to view the bond and the bond vibrational energy as coming from the idea that a bond is a spring. So here is the atom X, Here is the atom H, which is much smaller. And the energy of vibration is quantized, multiple levels possible, and the levels are defined by the following expression. Planck's constant, nu, Greek letter nu, is vibrational frequency. And n is an integer from 0 to 1 to 2 to 3 and so on. This is incidentally this defines incidentally what we call the 0 point energy. When n equals 0, the bond still has vibrational energy. And this is called the 0 point energy. And it reflects the fact that even at the bottom of the energy well, you're going to have some vibration. All right, so let's see how we might expect bond vibrations to be different with hydrogen versus deuterium. To do this, we need to deal with the fact that vibrational frequencies are themselves dependent on the force constant of the spring and the masses of the things on either side of the spring. And this is, I think, just classic mechanics, classic spring sort of mechanics. So the vibrational frequency for, say, hydrogen is going to be equal to 1 divided by 2 pi, describes some periodic nature of the frequency, 1 divided by 2 pi, times the square root of, and then we have F, which is the force constant. And then we have a ratio that is sometimes called, I think, the reduced mass. And this is where you take the mass of atom X plus the mass of atom H, and you divide it by the product of mass of atom X times mass of atom H. Okay? So this number is influenced by the mass of either atom. And because the mass of deuterium is 2 times the mass of hydrogen, the vibrational frequency for deuterium should be, again, same force constant, mx plus 2 times mh. And then in the denominator, we have mx times 2mh, where md is equal to 2 times mh, right? Let's choose, for example, let's let the mass of X be 12, like for carbon, and then m of H is 1, m for deuterium is 2. All right, so let's see how these differences affect the vibrational frequencies and therefore the energies, vibrational energies of a carbon-hydrogen versus a carbon-deuterium bond. So for a carbon-hydrogen bond, the vibrational frequency is, for reasons that will become clearer later, I'm going to bring the square root of the force constant out front, and then we'll leave in underneath the larger square root. For hydrogen, 12 plus 1 is 13. 12 times 1 is 12. In contrast, for the vibrational frequency of deuterium, the thing that's under the big square root is 12 plus 2, which is 14, divided by 12 times 2, which is 24. And so then if I want to compare the vibrational frequencies of carbon-hydrogen versus carbon-deuterium bonds, That's a simple matter of dividing those two square roots. The other terms being identical cancel out. And I can rearrange this to 13 times 24 divided by 12 times 14. And I can factor that into 2, and then I can factor that into 7. And so overall, the ratio between those two is 13, the square root of 13 over 7, which is around 1.36. So the vibrational frequency of hydrogen is, the vibrational frequency of deuterium is equal to the vibrational frequency of hydrogen times like 7 over 13. Okay, so you expect the vibrational frequency of deuterium to be lower than the vibrational frequency of hydrogen by that amount. And so if we compare the so coming back here to this equation of 0-point energy, the 0-point energy for deuterium is 1/2 times Planck's constant times the vibrational frequency for deuterium, and the 0-point energy for hydrogen is 1 divided by 2 times Planck's constant times the vibrational frequency for hydrogen. And we can use what we just derived above for a relationship between deuterium and hydrogen's vibrational frequency versus hydrogen's vibrational frequency, and come up with which suggests that the 0-point energy for deuterium is going to be lower than the 0-point energy for hydrogen. Okay, well, so who cares? So what about that? That's 0-point energy in a vibrational well. What does that have to do with kinetic isotope effects? And to understand this, we're going to draw a potential energy well for a bond, say between carbon and hydrogen. R is going to be the distance between carbon and hydrogen, and the x-axis is going to be energy. And we have our 0 starting point. At infinite distance, there's no interaction at all between carbon and hydrogen. You bring them close, and there starts to be energy lowering. You get them too close, and you get electron-electron repulsion, Pauli repulsion. The minimum here is the equilibrium bond length. But what I told you is that vibrational energy levels can never get all the way down to the bottom of that well. There is still a vibrational energy level for deuterium. That's equal to 1/2 times Planck's constant times the vibrational frequency of deuterium. This is the 0-point energy of deuterium, which is equal to 7 over 13 square root of that number times the 0-point energy for hydrogen. And then here will be the 0-point energy for hydrogen. And if we envision bond breaking as going from this bonded situation, sort of near the bottom of this energy level, equilibrium CH distance. If we envision bond breaking to be breaking that bond in a simple sort of homolytic fashion, bringing the two partners away from each other at infinite distance, then the activation energy for hydrogen is here, because this is our sort of no bond energy line. But the activation energy for the carbon-deuterium bond is here. Okay? And of course, this would describe breaking the bond, not making a new bond, and so this is not really a great description of the transition state. But basically, so we're going to approximate the difference in the activation energies for the carbon-deuterium bond versus the carbon-hydrogen bond as being this difference in 0-point energies here. So EAD minus EAH should be equal to, roughly, 0-point energy for hydrogen minus the 0-point energy for deuterium. Or, in other words, 1 minus the square root of 7/13. Now let's go back to why we said we expected to see a kinetic isotope effect. Activation energy of deuterium. Sorry, I shouldn't have moved that. Copy deuterium versus activation energy of hydrogen. We'll represent it that way. And then you can see how that's the same as the exponential of um, 1 minus the square root of 7/13 divided by kBt times 1/2 HVH, the vibrational frequency for hydrogen. What we're going to see is this number 1 minus this square root is still a positive number. So we're going to have the exponential of a positive number here. And overall, we're going to see that, that KH is going to be greater than KD, or in other words, that KH over KD is greater than 1. And if you plug in a value for sort of vibrational frequency for a typical carbon-hydrogen bond, which for a certain mode would be around 3,000 wave number, you can get out sort of a theoretical maximum kinetic isotope effect, maximum primary kinetic isotope effect, and it's about 7. Doesn't get much higher than that. Okay, so next time we'll talk in more detail about the origins of the kinetic isotope effect, and we'll actually consider differences in bond vibrations in the ground state versus the transition state, and we'll use that to rationalize where we might see kinetic isotope effects and where we won't.